All right, also, let me announce, the math club's gonna be actually kind of fun. This week, I think, well, it's fun, but this week it's gonna be kind of recreational. Eliza Gallagher and Neil Kaufman are actually gonna talk about Sudoku and some of its variants. And of course, as you might expect, that's pretty mathematical, so puzzles, math, I mean, how can you go wrong with an afternoon like that? So, think about being there. Okay, so this is the last thing, that we took off with last time. This is basically, sometimes it's referred to as direct product, not direct product, direct sum and tensor product community. So as you might guess, the proof of this and the proof of this are almost exactly the same. So let me sketch out number one. So if I want a homomorphism from here to here, then what you might do is let's say right. So to get homomorphic, go here. So let's look at the following. I want to find oh, okay. I'll go to now, this is the canonical sort of bilingual map. And what it will do is it takes a typical element, of course, of this cross product is something from here, something from here, right? And the something from here should be a indexed net. So here's a typical element of this. Of course, it goes up here to a single tensor here. And remember, this is finite. Almost all of these entries are non-zero or are zero. It's never tricky to do this because you just do this here. What do you suppose would be the corresponding element here? So I have a net comma B, and I want to get a net. Says me a net. What do you think? And this actually gives rise to some phi that makes the diagram. So that is to say, when you input a single tensor of this form, it'll give you out this net of tensors, right? Now, so we have this homomorphism here, right? Now, get another homomorphism from here to here. Right? from and how do you think you would do this? This is a little bit more complicated, right? Because this, a typical element of this is so a typical element of this is a net, again, where each TI is an AI tensor. Right? But what you can do is, of course, remember, almost all of these TIs are 0. And so that will give you a corresponding way to get this right here. Now, what you want to do is show that you want to show that these two compositions of the identity on respective domains. And really all you have to do is check the generators, right? So check the generators here, check the generating set here when you do this composition, and then the other composition did it as well. So this is actually a good exercise in verifying this right here, as well as verifying. It's easier to do that. By the way, it's easier to do this than, for example, if you just wanted to do this straight up, it's actually fairly easy to show that phi is onto, right? But it's a little bit trickier to show it's one-to-one. And that's why you might want to build this inverse map here. If you can find a short way to do one-to-one, I couldn't. But if you build the inverse map here, then that'll get you exactly what you. Okay, any questions? Okay, so let's look at the corollary that I gave you last time as well, and take care of that. Six, eight, 10. Let F be a free R module. And let me be specific with this. We'll say that F is isomorphic, the direct sum in some set of R. Because of course that's what free modules look like, right? And B an R module. Any R module doesn't have to be free. Then if you take F and it's with B, this is isomorphic to the direct sum of B. So when you take this free module and you tensor it with B, because it's free, this is some number of copies of B. And how many, you ask, because that's the only thing we need to know now, and that is the same size as the basis of F, or the index set that index free module. Okay, so let's prove this one. Well, this follows easily from previous result. Let's first write F by what it is. And there we go, right? Now, by the previous result, by the theorem that this is a corollary of, this is the direct sum R tensor B. And if you recall, we've already shown that this thing is isomorphic to B. So, and I should write isomorphism there. And then we'll get on. Okay. Questions? Okay, so in fact, when I edit these notes yet again, maybe I'll change this a little bit. I don't even know why I've got this as a section, but I call this section flatness. So I'm going to tell you a little bit about what this is. So flatness is, in a certain sense, flatness is a generalization of freeness. Okay. And I'll give you kind of an exercise to think about. It's similar to theorem 689 is kind of a good exercise in sort of playing around with the interplay between direct sum and tensor product. But in a certain sense, flatness is a generalization of freeness. There is actually, so flat modules have something like a basis. Obviously, anything that hasn't really strictly a basis is a free module. Flat modules have something that's a little bit looser than a basis. You can actually find a characterization of this in one of the exercises in the Bourbach key. They give these conditions for flatness, but I'm going to give you sort of the definition of flatness that is sort of more homological in nature. We saw last time in class, I gave an example of a one-to-one map of R modules, such that when you tensored it with when you tensored that with the identity of another module, you got the zero map, right? And so this is why tensors are only right exact. They may not preserve one-to-oneness. Flat modules are the ones that do. So we say R module M is flat if given any short exact sequence let's say 0, the induced is also exact. So the flat modules are the ones that actually preserve short exact sequence. A flat R module. Let me make a remark here. If given thing F make B such that F is 1 1, is also one. Because of course, the rest of that short exact sequence is automatically preserved with any tensor product. So flat modules are the ones that when you induce a one-to-one map with the identity map on M, it remains one-to-one. Right. Okay, so here is I'm just going to give you a couple of theorems here, mostly without proof. Theorem. Six, 9, 2. Let M be an R module. For the following conditions, we have A as B plus C. A M is free. B M is protective. C is flat. And none of these conditions are reversible in general, right? Whether or not they're reversible depends on the ring, right? So for example, if the ring I give you is in fact a field, then these are all three equivalent, as a matter of fact, right? Because if it's a field, everything's free, right? So let me kind of give you a sketch. And I do mean a sketch because I'll leave it for an exercise to show the details, right? But suppose and I'm going to bootstrap back to the projected case here. Suppose you have a one-to-one map here, and let M be free. Now, again, I'm going to be a little softy here, and I'll let you think about putting the details on this. But I'm going to sort of use this notions that we've done before. So what does it mean to be flat? It means that you have to preserve one-to-oneness. We have to show that F tensor 1M from A tensor N to B tensor is still one-to-one. That's what it means to be flat. We need to show that any injections preserved. Well, notice that A tensor M is isomorphic. A tensor R, the direct sum of R. And here we have two. And this is, of course, isomorphic to the Insert the direct sum. All right. And this is, of course, isomorphic of this direct sum theorem we get. And just a bunch of copies of A. And this is just a bunch of copies of B. Now that's kind of my hint here. You can use this F, right, on every coordinate here. Remember, this has all zeros except for finitely many. And notice that this F sort of induces on every coordinate a one-to-one map, right? So this is, of course, actually different than this, but they're isomorphic. So see if you can use this kind of hint to show that this also has to be one-to-one, right? And then that will get you this. But how would you get it? And of course, by the way, we already know this from earlier class, right? So how would you get that projective implies flat, which is the missing piece of this? Well, once you've totally conquered this, right? How can you bootstrap that to projective? Well, if you consider the projective case, remember, if M is projective, then it is the direct sum free, right? So there's some other module N such that M direct sum N is projective. See if you could take both of these, put them together and deduce that. So that's something for fun. And here is a corollary. Once you've got this, excuse me. Let MI be a family of R modules. Then the direct sum of MI, by the way, this is very similar to what we have projected as well, is flat. If and only if MI is flat for all I. So in other words, the analog of the projective result works here as well. Okay, any questions? Let me ask you this. How many of you, I know if I asked this before, but I forgot the answer. How many of y'all have seen like the canonical forms in, like a linear algebra class or some other class? When you take a square matrix, you maybe look, how many of you have seen your canonical form before? Rational canonical, there are various. Ever heard of Smith normal form? Did they ever talk about any of that stuff in linear algebra? Well, so we're going to talk about that here a little bit. And it's funny because all these things that if you see this in 8530, how many of you all are in 8530? So have you talked about eigenvalues and that kind of thing yet? Not yet. So my guess is, can't swear to it, but my guess is in 8530, if you do the canonical forms, you might do this through something they might call generalized eigenvectors, generalized eigenvalues. We're going to do this from the point of view of modules over principal ideal domain, right? It's amazing how this comes out. I hope that for some of you that are planning to take the algebra qualifier exam, that this might be helpful because I'm going to do the theory, I'm going to develop canonical forms, and then I'm going to get my hands dirty. And we're going to do some, I'll show you actually how to, if you're on a desert island and you really need to find canonical form for a matrix, then you're in the right class. So So let's look at this here. Chapter 7. Modules over APID in the canonical. And actually, I find it kind of amazing. Now, the easiest counter ring in the world, especially for a guy like me that likes commutative rings of identity, the easiest ring in the world is field, right? The only ideal is 0. The only proper ideal is 0, right? You don't have to worry about zero divisors or even factorizations. Everything's a unit. It's not 0. And the modules over a field are incredibly easy. They're all free. So every module over a field is a vector space. So if you want to talk about module, and so this is why I think that when you think about this from an algebra point of view, it trivializes linear algebra, right, in a certain sense. Because when you talk about vector spaces, all you need to do is specify the field and specify how big dimension-wise you want the vector space to be, and you know everything, right, from a certain point of view, right? I want this to be a vector space over R of dimension n, Rn, that's it, right? I want to have a vector space over R that's got countable infinite dimension. It's countable number of copies of R's direct sum in the story. Gotta love fields. They've got very easy modules. So one might think, as you walk away from fields into more general rings that are not as nice, what does that do to how wonky the module structure is? Right? Well, what's the first step away from a field? First step away from a field probably is everybody's favorite basic ring, the integers, right? I mean, the integers are what starts it all. The integers are very nice, right? And one of the reasons the integers are nice is this. It's principal ideal domain. And so what makes the principal ideal domain magic? Well, a big source, take the integers, for example, right? What are the submodules of the integers? Submodules of the integers are the ideals of the integers. Agreed? But the integers is a principal ideal domain. That means that all of its submodules, ideals in this case, are generated by a single element. So all the submodules of Z are free, right? Now, not every Z module is free, right? Z mod 2, Z module, not free, right? Q, a Z module, not free, right? But every submodule of Z is free, right? And this, you might think this is modules over the integers, but there's actually no harm in generalizing to a principal ideal domain. Right. So one might think, in a certain sense, that PIDs are the nicest kind of rings that you could ever encounter that aren't exactly that aren't fields. And so we're going to look. So we're going to start with this, a little short thing. And actually, I'm not going to do a lot of details. I'm going to do a few proofs here and there. My guess is you've seen this before, or at least familiar with it under another guise. I bet Matt did in the first semester. I bet he did the fundamental theorem of finitely generated abelian groups. Y'all remember that? And he did he do invariant factors and elementary divisors and all that. He might not have told you this at the time, but this is what he did. What he did was basically he was doing finitely generated modules over a PID. Because if you look back at whatever he did, none of it, I'm sure, depended on the fact that it was the integers as opposed to just being a general PID. And of course, finitely generated abelian groups are finitely generated modules over Z, and Z is a PID. So let's look at the structure of finitely generated modules over PID. So we're going to do this first. But as we get involved in the structure here, I got to tell you a few Yeah, so I'm going to define some things in this theorem. So I'm going to give you a theorem. So it's going to be a statement. There's going to be some definitions in it too. In this section, in this chapter, certainly R will be commutative with one. And in fact, you can default to PID unless I tell you. I'll probably be very specific if it's not a PID. And of course, all modules are unitary. Theorem. Seven point 1.1. Let A be an R module. Well, let R be a domain. So here's my first departure for PID. The first view of this theorem is true for any integral domain, and then I'll specialize the PID later. And an R module, little a in a, some element, and whatever that crazy German thing is here. DA, I called it. I don't know why in the world I did that. This is the set of R and R such that RA. So this funny little, actually, you know what I'm going to do? Oh, I am going to. I don't think I'm going to get burned on this, so I'm just going to change this to. This is supposed to be short for annihilator, right? Maybe that's a little bit more suggestive terminology. The annihilator of A is everything in R that kills A, right? Multiplied by A and get 0. This is sometimes called the annihilator of A. Part A. The annihilator of A, any element of the module, is in fact an ideal of R. I'm going to call this capital A of T. This is a subset of A consisting of such the annihilator of A is not 0. Is a submodule of A. The important thing here is that actually R is an integral domain, and C when I take R and mod out by the annihilator of A, anybody want to guess what that is? This is isomorphic to RA as an R module. So let me add an assumption here. And if R is a PID, so we only need domain for the previous three. We also have number D, let me go for a little clarity here. P, of course, is a prime, so it generates maximal ideals and PID. Here, of course, we're assuming that we're sort of assuming here that R is a PID that's not a field, and you'll see why in a moment. If PIA equals 0. So PI at PI times A equals 0, which is equivalent to saying that PI is in the annihilator of A, and the annihilator of A is the ideal generated by J for some J between I and 1. No, I guess that could be 0. And I'll ask you about that. And E, if the annihilator of A is P to the I, P to the J, A is not 0 for J less than I. Okay, so let's prove this. Okay, the annihilator of A in R is an ideal. Okay, well, so let X, Y be the annihilator of A, and let R be an R. Then X plus RY A, well, this is XA plus RYA, but X and Y both kill A, so this is 0, which now means that X plus RY kills A. So the annihilator of A is an ideal. Oh, actually, if you want to pick on me a little bit, I did sort of skip over one detail. Does anybody see the technical detail I skipped over in my little short proof? So what I used is if I had two things in the annihilator, something in R, and X plus RY is still in the annihilator, that means it's an ideal, right? But I skipped over an assumption. I really wanted to pick on myself, and I often do. Non-empty, very good. That's right. Because to apply this, I have to have non-empty. But is this going to be a problem? 0 is certainly in the annihilator. So okay, we're good to go on that. Okay. By the way, you should notice that part A didn't even depend on integral domain, right? That this statement is true anyway. I think this one will though. AT, by the way, this A sub T is sometimes called the torsion elements. This is a set of everything that is killed by something other than 0, right? So A1 and A2 and A2. Then there exists non-zero X in annihilator A1 and Y in the annihilator of A2. Okay. Notice that AT is also not empty. Anyway, tell me why. Why is AT not empty? because you've got the zero element of the module, and we're assuming that R is an integral domain, so at least it's got a multiplicative identity. And 1 times 0 is 0, so we're good to go. Right? This thing is not empty. Let's let X be in the annihilator of A1, Y be in the annihilator of A2. We need to show that if R is an R, then X plus RY annihilates, or I'm sorry, yeah, X and Y are now. Let's see, A1 and A2 are here, right? So we need to show okay, so we've got A1 and A2, they're torsion elements. That means that there's a non-zero X that kills A1, there's a non-zero Y that kills A2. What do we need to do? We need to show that if R is an R, then a non-zero element of R annihilates A1 plus R and A2. Right? And then that'll show that an arbitrary, given A1 and A2 and R, that this will be in there. We know that 0 is annihilated by something non-zero, so this is not empty. Candidates for filling this. Right. Note. A 0. Now here's the rub. You have to kill this with a non-zero, right? But see, this is where we actually need a domain. And as R is a domain, and X, Y are non-zero, then X, Y. And so we're good to go. This is a submodule. This is similar to a homework problem you did, and in that homework problem, really the problem is in the homework problem that generally speaking, if R is not a domain, you don't expect this AT to actually be close to addition. Okay, how about this one right here? Part C. Well, define phi from R to RL. And let's do this in the easiest way I can think of. Phi is R module epimorphism. Right, after all, it's clear, isn't it clear to you all that this is onto? Because the typical element of this looks like little RA, and R will go to little RA. Right? And kernel of phi. What is the kernel of phi? It's the annihilator of A. It's everything in R that kills A. And so now apply the first isomorphism theorem. This homomorphism is onto, and so R mod the kernel is isomorphic to the image. Got that okay? Okay, so far, so far we've only needed domain really for part B. We are going to need a PID for these parts. Let's look at D. If I'm sorry, P to the I times A is 0, so PI is the annihilator of A, then the annihilator of A is P to J. Any ideas on how to prove this function? So let's suppose that the annihilator of A, well, oops. Suppose PI is in the annihilator of A. And of course, the wild claim is that the annihilator of A is a power of P that is perhaps lower than I. Okay, so what is my blanket assumption here? P is a prime and R itself is a right. And we already know from our previous work that this is an ideal. Right? This is an ideal. And since R is a PID, what can I conclude? Generated by X. Right? Something, right? I agree with that? Yeah. Okay. Now, we also know that P to the I is in here. Right? As P to the I is an element of X, then there exists R and R such that Rx is P to the I. And I'm fixing to use one of my favorite words here in a moment, I think. So how does that help? Correct. R is a PID, hence you have. Right. So this is two factorizations of this element, right? On the right side, we have P to the I, on the left side, we have Rx. Rx, I'm a little fuzzy on, but I do know this much, that this is a prime factorization consisting only of PI. So by uniqueness factorization, well, say prime factorization, I can only conclude that X is equal to a unit of P to the J, where U is a unit and because I know by uniqueness factorization that this is some power P that's less than this. By the way, what happens in the case that X is P to the 0? What does that mean? What happens? If you remember when I first wrote this theorem down, I wrote, I said, no, it can be 0. What happens? What happens there? Let me finish this idea here, and then maybe we get this. The ideal X, which is the annihilator of A, is the ideal generated by each A. What happens if J is 0? That's right. That means the annihilator of A is everything. And what does that mean about the element A? It means that A has to be 0 because the module is a unitary module. So what you're saying is anything here kills it, including 1. And so if 1 kills it, gotta be 0. Concentrate, I think doing D might make E a little bit easier. Think about that and we'll pick this up next time. Any questions? Any questions? How about you, Rebecca? Any questions out there?
No, I'm okay. Thank you.
All right, well, y'all have a good one and we will see you on Friday.